Welcome, everybody, to another of the American Nuclear Society's Risk-Informed Performance-Based Principles and Policy Committee, RP3C's webinars. My name is Prasad Kadambi, and I am chair of RP3C. The purpose of RP3C is to help modernize ANS standards. Modernization has come to mean that risk-informed and performance-based methods are employed to overcome the difficulties that we all know about with purely deterministic and prescriptive methods. We have been calling these methods RIPB approaches, and this has received special significance due to the enactment of the Nuclear Energy Innovation and Modernization Act. There's a lot of guidance available for RIPB approaches, but most people have not had reason to become familiar with the guidance because the conventional approaches still dominate most things that we do, including standards development. So right now, ANS, with all the recordings we have of these community of practice presentations, where people who are actually involved in the implementing or who are doing RIPB in their work share their knowledge and experience. So today we are going to hear a presentation based on work that Svetlana Lawrence of INL and I did over the past more than a year. And, but she is unable to join us today. So she has made a recording of her part of the presentation. And that is what Pat will be playing. And after that, I will take over and answer any questions that are posed and also answer any questions about the part of the presentation that I will make. So Pat, go ahead and start Lana's presentation.
Hello, everybody. My name is Lana Lawrence. Thank you for being here and for your interest in this presentation. I work for Idaho National Laboratory, where I am leading a research area called Risk-Informed Systems Analysis. And this research is part of a larger program. It's a Department of Energy sponsored program called Light Water Reactor Sustainability Program. And the program is directed towards making our operating fleet more sustainable in terms of mainly economic sustainability, but we also address issues like obsolescence and aging of our materials and structures. So it's a very large program, has been around for many years, and it helps. Again, it makes a significant difference in sustainability of our operating fleet. So today I am going to talk about benefits of adopting risk-informed performance-based approaches for operating reactors, potential benefits. I am a member of RP3C community, and I am very happy, honored to be here. And again, thank you for your time. This slide presents relationships between deterministic and probabilistic space. So since WASH 1400, the risk insights from PRA models, they play a very important role in the plant operations and also in the reactor oversight process. And we understand from plant PRA what is important to safety and also what is less important, so we can focus our resources on the really important things. And deterministic and probabilistic space, they are connected to each other. So from deterministic analyses, we understand, we develop a scenario that provides us understanding in probabilistic space how we can calculate frequency or probability of that sequence to occur. We use probabilistic space to inform decision making in the regulatory space, and we rely very heavily on PRA model for risk-informed applications. And those applications proven to be very successful, and they are saving a lot of money to the industry. And there are a few largely known, the 10 CFR 5069, that is an engineering program for system classification, allowing to reduce regulatory requirements for components that are non-significant, that are safety related but not risk significant. The risk-informed technical specifications, the risk-informed in-service inspection program. So all of those programs are designed to save operating fleet significant amount of money, and all of those programs to the various extent rely on PRA model. So again, PRA model has been used successfully. However, we understand there are limitations of PRA model, and we exploring ways to expand risk-informed applications in the performance-based approach, and where performance-based can be used hand in hand with risk-informed approach to support sustainability of our operating fleet. So why we're talking about performance-based and what are the difficulties? Well, the probabilistic space has certain limitations that can be that cannot really be overcome just because the way we design PRA and the way we approach PRA. So first, the PRA model is based on the dedicated set of scenarios, and those scenarios are typically bounding scenarios. So we can use one scenario to account for multiple different sequences, for multiple scenarios. And it was done intentionally from the very beginning because of the computational power limitation, because of uncertainties. So there is this decoupling between deterministic space and probabilistic space, and that is one of the limitations what probabilistic space of PRA can help us with. Also, we are only looking in traditional PRA for lightweight reactors. We are measuring risks using surrogate matrix, which are core damage frequency and large early release frequency. Well, risk at the plant is not necessarily only core damage, right? So some scenarios may not go all the way to core damage. However, that is still risk. So think about, let's say, spent fuel pool and rod waste, and those calculations that are not necessarily associated with the core damage frequency. So we cannot use PRA model just because those risks, they're not modeled on PRA, just because that's not the purpose. So again, we started thinking, well, what if we use performance-based approach to supplement our reliance on risk-informed approaches? So the idea of combined risk-informed performance-based approach is not new. The Commission specifically defined performance-based approach in CRM CIK 98144. And the performance-based requirement is one that is relied on measurable outcomes. And in turn, we gain flexibility for plant operation. So if you read CIK 98144, the white paper, how we call it, on risk-informed and performance-based regulation, we see the 5 large points in this RIPB approach. The first, it focuses attention on the most important activities. So that's what we get from the PRA model. It helps us to understand what at the plant is important. It also establishes objective criteria for evaluating performance. And right now, we do have criteria in terms of delta CDF and MSPI and some other criteria, but they are not robust enough to cover all the performance, different set of performance and different operating conditions. So it also allows to develop measurable and calculable parameters for monitoring system and license performance. So that is where performance-based approach becomes important, because it's really hard to use delta CDF as a single risk measure for everything in the plant. So some parameters like MSPI, it's a mitigating system performance indicator, that allows us to look at the system performance. However, even MSPI is not live indicator, because it looks at past performance and history performance, at unavailability, reliability parameters. And if you look at the concept of unavailability and reliability, it's a looking backward parameter, right? So it's a historical measure of how a system or a component has been performing and what is the probability of failure. Well, we need something that is measurable and observable live, today, every second, every minute, or every day. We want to understand how a system performs. Well, those parameters do not exist in PRA space, because PRA, it's a snap in time. It's not dynamic. It doesn't understand time. It's just one single cut in plant performance in one time, and looking backwards, you collect your data to plug in PRA to understand reliability of your system. However, again, it doesn't give you any representation of your current today performance. And the next bullet point, number 4, in the SECI, in the white paper, it specifically tells us that risk-informed performance-based approach provides flexibility to determine how to meet the established performance criteria in the way that encourages and rewards improved performance. And lastly, the focus is on the results as the primary basis, as the most important parameter for the regulatory decision making. So again, those ideas that were outlined in 1999 when white paper was issued, those ideas are still valid today, and they're even more important today because our operating reactors, they do experience economic struggles. And this flexibility is gained from, or can be gained from, risk-informed performance-based approaches, would significantly help benefit the economical performance of our plants. So a few specific benefits from performance-based ideas. So the performance-based approach is based on the idea of real-time observations, and those real-time observations can be used to validate the accomplishment of the defined objective for a system performance. And that is opposed of reliance on prescriptive rules for system manufacturing or for system performance. So instead of saying, well, you have to test this system twice a year, right? So instead of that is a prescriptive rule. Instead of it, we can say, well, the system shall produce 250 gallons per minute to meet the functional requirements for the system to accomplish the function that is designed for. The performance-based approach also can be used for design activities, so it can be used for licensing activities and oversight activities. The idea of margin between the current operational state and the limit state becomes very important. And this margin represents the acceptance criteria or success criteria in PRA terms. And the performance objective is categorized by the requirements that are associated with that minimum accepted margin, again, between the current state and undesired state. And the requirements management for system performance that is expressed in terms of margin, it takes into account not just nuclear safety, but it also takes into account economic performance, economic requirements, and let's say investment protection requirements. So there are larger set of objectives that could be assigned in a performance-based space rather than just nuclear safety. And we understand now it's important because our latest closures of nuclear power plants were not driven by safety concerns, right? They were driven by economic sustainability and economic concerns. So the economic concerns and considerations become more and more important. And the regulatory framework can also inform use information from performance-based approaches in addition to currently used risk-informed approaches, and that would allow to reduce amount of inspections and time spent by the nuclear power plants to prepare for those inspections, and regulator can focus on the more important functional level of plant performance. This slide talks about the idea of, well, what if we step back and instead of creating bounding scenarios and rely significantly on assumptions and different conditions that we prescribe at the PRA model, kind of draw a box in PRA model for each scenario. What if we run multiple scenarios, all of the scenarios? Because right now computational power allows us to run multiple scenarios. And this dynamic approach allows us also to account for timing, not just the snap in time, but we also understand how scenario progresses through the event, right? So how plant conditions change during the scenario progression. And again, the benefit here, if we use the dynamic approach and we run multiple scenarios, now we don't have to define the bounding condition. We don't have to use so many assumptions that we use now that put us in this conservative state at the end, as a conservative result. So I talked about safety margin a little bit. I mentioned safety margin as a basis for performance-based approach. So if you think about the safety margins, it's not a new concept. In structural performance, in structural world, that has always been employed, right? So we have the loads that we understand, and we have a system capacity. And ideally, you want to keep load as far away as you can from capacity. Well, and that is the margin. So the distance between the load and capacity, that is your safety margin. Again, when economics become a concern, you don't want to over-design your system. So you do want to keep them reasonably far away, but you also want to make sure you don't spend extra money to design for extra capacity unnecessarily. And this margin exists, for example, in concrete performance. The crack size is the measure to evaluate degradation of margin. The same with metal performance, or let's say in component health, the remaining useful life can be the measure of margin. And similar in 10 CFR 54, the aging management, we can establish the available and acceptable level of margins that we want to monitor for aging as an aging management program. So instead, again, an aging management, instead of saying we have to inspect underground piping every 10 years and 10% of piping needs to be inspected, which is really expensive. Well, maybe we can design another matrix that tells us where the system condition is now and where is the undesirable condition. And that margin we can use as a justification for performing or not performing actions associated with the aging management problem. So when we talk about performance-based approach, so what exactly does it mean? And here I'm talking about just a short example. So in traditional way, we're saying we need to inspect the selection of piping, and we prescribe details and dimensions and materials and what to use, what non-destructive examination use, what section, what area of plant needs to be examined, and the frequency. These are all very prescriptive approaches, and if you read the GAL report for aging management programs, they are very, very large volumes of the requirements associated just with aging management program. So the performance-based approach is different because it establishes objective criteria for evaluating the condition. So, and then we develop measurable parameter to monitoring the condition. And then licensee determines how to meet those established criteria. So the regulator has a say-so in this process because the regulator accepts the parameters that are established for system performance. The regulator also has to agree to the objective criteria for evaluating the condition of this component. But then it's on licensee to control how to meet those criteria. And licensee chooses more efficient way to meet the same criteria. So again, it's a partnership between the regulator and licensee, how to ensure the adequate performance of the system, but in the most efficient way. And benefits are multiple here. It provides the flexibility in the way how to meet those established performance criteria. It focuses on the results as the primary basis for the regulatory decision making. And again, licensee has more control over the results with the NRC oversight being secondary, being focused on the higher level. And that is put in a simpler form. So we're saying that the system hierarchy, we start with mission, and mission of the system is the top priority. And then we decompose the mission, which is protect public and protect environment. We decompose it to safety functions of the system. And then we determine, okay, to meet the system functions, how system should perform. And then the components are designed and then monitored based on their capability to accomplish the system performance. And right now, we have very few requirements at the mission level. It's basically just the overall CDF, LRF, and defense and gap. And then we kind of drill down, so the more detailed requirements are applied at the system function, and then the more requirements are applied at the system performance level. But majority of current requirements from the reactor oversight process actually applied at the component level. And that goes from the manufacturing of component, designing system, and the monitoring performance. So most of the requirements belong to here, to the component level. Okay, so if we compare the system hierarchy, it actually resembles really well the hierarchy of the reactor oversight framework. So we start with the mission, again, protect public health, and we decompose the mission to strategic performance areas, and those are decomposed further in cornerstones and supported by cross-cutting areas. So the idea here of performance-based approach, what if we focus our attention on the top level of hierarchy, on the what we need to ensure. We need to ensure the mission, and we need to ensure the fundamental objectives of functions, right? So reactor safety and radiation safety and safeguards. But how? That is where licensees could gain more flexibility as to how they accomplish the what. So all this bottom level could be left, maybe not entirely to the licensees, but licensees could have larger flexibility with the deciding how to achieve the performance objectives at the system performance level and certainly at the component level. So right now it's a good time to think about performance-based approach for operating reactors, because that is the approach that advanced reactors are moving towards. If you're aware with the licensing modernization project, the performance-based approach is an essential part of that project, of that approach, whereas the risk is no longer measured as a core damage frequency. Well, first, because it may not be applicable to all operating reactors or to all the new reactors compared to the operating reactors. And the risk is measured something that is phenomena-based, so it's in dose. And the frequency still remains in place. So frequency is there, it doesn't go anywhere. But again, the consequence is not measured in a surrogate metric like CDF and LORF. The consequence measured in something that is physics-based, dose. The idea behind LNP is the heavy reliance of phenomenological modeling and simulation, which reduces the reliance on assumptions and uncertainties. And the way we can think about for application of licensing modernization project to light water reactor, you can think about, well, what if we apply the same approach, the same methodology, but not for advanced reactor, but for operating reactor? Well, one of the benefits is the selection of design basis accident. Right now, large break loca is one of the design basis accidents prescribed in chapter 15. Well, if you use LNP approach, the large break loca will not become a design basis accident. And just think about how many requirements for plant system performance stem from the large break loca design basis accident. So if that is no longer a design basis accident, but becomes beyond design basis accident, the requirements on the emergency cooling system can be reduced, the requirements for emergency diesel generator startup from 10 seconds, that can be reduced, and that on itself provides significant savings, could provide significant savings for the operating reactor. And LNP could also allow you to use safety margins expressed in measures other than core damage frequency. So risk can become let's say time can become a measure of risk, or defect size or flaw in the system, in the pipe or a component can become a measure of risk. And again, margin to acceptable radiation dose, that becomes your performance measure, not just reliance on CDF input. Couple of examples for cost savings opportunities other than just reassessing our design basis accidents. So equipment maintenance. We are, as an industry, we are transitioning to performance-based equipment maintenance, and we're able to do it fairly simple for non-safety related components because there are no tax-back requirements associated with the non-safety related system. But the same approach, if you think about it, can be applied to safety related systems. Those are just mechanical systems. There is nothing different between them physically. It's just we dedicate safety-related system and we put it in one bucket, and non-safety related system go into different bucket. And that's how we assign the level of requirements associated with each system. But if we think about the performance-based approach, if we monitor the system performance, it can be done similar way, regardless safety-related, non-safety related. So we understand the condition of the system, and then we evaluate the progression of the system health or degradation of system health over time. And we understand where the margin is between the current condition now that is observable and the undesired state. So what we want to monitor, this remaining useful life or remaining acceptable condition of the system. And we want to schedule our maintenance according to that margin that we establish and undesired condition and undesired degradation of the margin. And this will reduce unnecessary maintenance that is done too prematurely, that we're required to spend resources and time. And it will allow us to understand the condition of the system as we speak every day. We understand where the system is on the health scale of the system and how that system contributes to the overall plant health condition. Another big area for cost savings is a subsequent license renewal or aging management program in general. The subsequent license renewal is just a aging management program, if you think about it. So there are three processes in the current license renewal aging management review: is the scoping, screening, and aging management review. So if you read about the scoping, basically all safety-related components go inside the scoping, are in scope for aging management program, as well as many components that are committed to in different programs, either your fire program or seismic program, and then not to mention defense in depth. So the scope is very deterministic. Everything that you have committed your plan to in various either risk-informed application on different programs would become the scope of your aging management program. Well, but we can look at it differently. We can look at the scope of the aging management program based on the need of a component to fulfill the top level function, to fulfill the functional performance of the system. And you may see on many cases the scoping being significantly reduced because a certain component, even though it's prescriptively assigned to the system or the safety-related function, it doesn't contribute significantly or it doesn't contribute at all to performance of that function. And the aging management review program, so instead of prescribing how many times we need to inspect a certain pipe or a certain component and percentage of the equipment that needs to be inspected, well, maybe we can life monitor certain system and ensure the current performance of the system is adequate, which would eliminate the necessity to do prescriptive inspections. A few other opportunities listed here, I will not repeat them all, but the idea is here that we can use, for example, equipment qualification can be redefined from MQA1 requirements to using performance-based options for equipment manufacturing, equipment testing, equipment maintenance. Same with the specification management. So instead of relying on the outdated specifications that were originally designed at the very beginning for the plant, so now we're trying to replace a system at the plant, and we're still relying on the specifications that were developed for the original system. Well, instead of prescribing parameters for each component and each system part, maybe we should focus on the system performance and allow vendor of that system to find the most efficient way to achieve our functional performance that we need to achieve. And this would allow flexibility, vendor flexibility, and it would allow us the flexibility to choose from different vendors, different systems, and we expect that it will provide significant cost benefits. Now let's talk a little bit about the standards. I will start with the ASME Section 11 Division 2 standard, which is a risk-informed performance-based approach compared to the Division 1 standard, which is risk-informed in-service inspection program. So Division 2 program goes hand in hand with the LMP-like approach. It doesn't mention an LMP approach, but it is implied that the performance of a system and performance of each component shall be guided by the overall plant performance. And we call it reliability target. The plant level targets are informed by expected component performance, but the component reliability target is set to ensure that overall plant performance is adequate and corresponds to licensing requirements or investment protection requirements or whatever set of requirements the plant selects. So again, if you think about the LMP approach and frequency consequence curve, you start with the plant level. The dot on the FC curve represents the plant level performance or plant level reliability target. And then you decompose your plant level into the system performance and the subsystem performance level, and all the way to component performance level. And if you think about, there are millions of ways to achieve your plant level performance by varying your component level performance, meaning that you have a lot of flexibility at the component level to choose your materials, to design your plant, or to choose your monitoring strategies for component performance to ensure that plant level targets are met. And that's where it becomes really important to establish the this bridge, this connection between the function and the component health, between the system health right now and the functions that the system is supporting. So this numeric reliability value or reliability target, it's not observable. So even though the ASME standard requires you to establish the reliability target for each component, well, if you think about it, I cannot really observe 2.5 E-6 as a reliability target. So we need to establish a performance criteria that I can monitor. Either, let's say it's a wall thickness, 0.5. So that is something that I can measure using multiple non-destructive examination methods, and I can propagate them through modeling and simulation to predict what will happen next and remaining useful life of that component. So the risk-informed performance-based approach is the solution here. That is the bridge between the observable performance, observable, measurable, calculable performance of a system or a component and the resulting reliability of that component that needs to be established. And I will turn it to Prasad now to talk about the ANS standards. Thank you.
Okay, Pat, I guess you'll take over the slide presentation now from slide 17. Or, okay, yeah, there you go. That's it. Thank you. So, everybody, the key takeaways from Lana's part of our presentation is to establish that margins are an essential aspect of incorporating a performance-based approach. She pointed out many opportunities for cost savings in operating reactors licensing if the performance-based aspects are included with the risk-informed practices for meeting requirements. And these requirements may be related to the continuing design decisions with operating reactors or with the regulatory decisions also. She addressed how the application of these ideas can be extended to standards using the ASME RIM program as an example. The same ideas are equally applicable to ANS standards, and I would like to offer some examples of that. What you see on the slide here is related to ANS 2.26 on categorization of SSCs for seismic design. Now, this standard was issued way back in about 2005. I consider it to be the first risk-informed performance-based standard. It addresses the seismic performance of systems by dealing with what Lana called as the difference between an existing state and the limit state. So this standard specifically identifies limit states and how you reach acceptable performance by making sure that there is enough margin. Design categories are established for the SSCs based on the expected frequency of reaching the specified system states. Next slide, Pat. So this slide shows how ANS 226 actually works. 226 actually just provides an architecture for the application of several other standards. And these others include two ANS standards, 229 and 227, but also a standard from the American Society of Civil Engineers, 4305. So this is an example of how we can build risk-informed performance-based approaches into suites of standards. Next slide, Pat. So the next standard I want to talk about is 30.3, and this has to do with the risk-informed performance-based design of LWRs. So this was recently issued just last year, and I think it's the most recent ANS standard. It is now being reviewed by NRC staff, and we have received the first round of comments from NRC. This standard represents an example of implementing the hierarchical requirements management that Lana spoke about. The most important point from the point of view of the user of ANS 30.3 is that it focuses on a performance-based decision-making process. It calls for a formal decision analysis process, and it is structured along hierarchical lines. And in order to maintain the rigors, to have the rigors needed for regulatory compliance, this whole the structured decision making is formalized. The ideas related to risk and margins are actually implied in the way that the user of ANS 30.3 makes specific decisions among the choices provided by the standard. And the thing is that this formality of the decision analysis process is because, without such a process, decisions made over the evolution of a design may become ambiguous, conflicting, or inefficient. And this is from actual experience that, many aspects of the standard were developed. Next slide, Pat. So this slide deals with a standard that is now under development, and it has to do with using plant simulators for other than operator training, as much of it happens right now. This standard, in my mind, offers a connection between model-based systems engineering practices and the current use of simulators that is not associated with training. So ANS 3.5.1 represents an example of implementing a graded approach to requirements management. So, the user of a standard who wants to use RIPB ideas will, in my mind, likely choose use type 3, 4, or 5, that is as an engineering simulator or a simulator for plant hardware connected and for non-operator training. So, but the requirements in the standard, because this is a voluntary consensus standard, they're not binding unless the user of the standard invokes the standard for some purpose, generally if it is related to meeting a regulatory purpose. So, that way, the user of the standard has a lot of flexibility in its use, and we expect to submit this for approval, for endorsement to NRC. And what we would plan to do is show how it conforms with the Commission's directions in SRM to SECI 98-144, and that the staff should use the Commission direction as the basis for the review. Next slide. So, in summary, although the Commission called for changes in the regulatory approaches almost 25 years ago, the conventional regulatory practices really are what most applicants and licensees encounter when they interact with the staff these days. And we are finding that to be the case with ANS 30.3. industry itself has been talking for some time about modernization, but industry generally identifies modernization, especially after the Nuclear Energy Innovation and Modernization Act, as something that is primarily risk informed and ignores the benefits of a formal performance based enhancement to these existing approaches. And there's no benefit from the existing NRC issued guidance on performance-based regulation. But I would think that these days, with activities such as the license renewal of Diablo Canyon, there needs to be a shift of the focus to from just risk considerations to one that includes formally defined safety margins, and especially with regard to implementing the requirements of 10 CFR Part 54. So I think there's a confluence of needs between, operating reactors and the standards that we are working on in ANS. That concludes the presentation itself. There are a few questions on the chat. I'll try to pick up on these. Pat, can we go through the questions raised one at a time, please?
Most certainly. So I think our first question is by Ralph Hill, and he asked to clarify why there are two reliability targets, one for hazard initiating event and one for plant reliability.
Well, okay, Ralph, I have to plead ignorance in terms of answering your question, because this is really, something I think associated with the ASME standard, and unfortunately Lana is not here, and she would be the one, because she's more knowledgeable about it. In fact, I would think that you would provide a better answer, than I could, if you thought about it. But I just don't know. So we'll just move on to the next question.
Well, Prasad, before you do, why would there be any limit? This is Jim August. Why would you limit it to having a single target? Or Ralph, if you're available still.
Well, I'm not sure, Jim. Again, as I say, because Lana is not here, and I'm not sure there's anybody from the program. So we'll.
I just don't see it as an issue personally, but that was my thought.
Okay. Well. Let's try to answer the questions that we can, if possible, and we'll get back to Ralph and you, when we know, when we get someone qualified to answer it. So.
Yeah, and I think the rest of our questions are from Jim August, and they're a combination of comments as well as questions. And he had said that many of the proposed PB criteria, like remaining life, are in reality very problematic for use in practice. They are not well defined enough to allow objective use. While their intended use is understandable, they are well developed enough today for many or most applications for objective use. What's the resolution? Says to work on it. So I'm not sure that there's really a response to that. Prasad, I'll let you take it.
No, I would like to respond to that, Jim. The fact is that this is where the actual consideration of margins comes in, and where finding the right performance parameters and the acceptance criteria of those parameters becomes the key issue. And I would refer anybody right now, the existing guidance on this that to some extent addresses your question is in Appendix C of ANS 2.26. That appendix was prepared to identify natural and constructed parameters. You can find appropriate parameters depending on the types of objectives that you're trying to accomplish. And this is part of the reason why it is important as part of a performance-based approach to construct an objectives hierarchy. So that's part of the answer to your question, Jim.
Well, I asked that question with malice, if I should apologize, because you can look back over the past 40 years, and a good example is the non-nuclear part of the plant, where you've got the detection of what's called partial arcs, basically, within the generator section, and the evolution of the technology to objectively measure those and relate those to the remaining life of the insulation windings. Went from something that was purely research in about 1980 to really in full implementation in 2000, and highly effective. It took 20 years of pretty intense research and development to do that. I see that across the board in many other areas. If you want to be objective about these remaining life measures that we're talking about here. Doing life extension at nuclear plants, you keep hearing the remaining life estimates come up, and to me, they're nothing more for most of them than somebody grabbing some idea out of the sky and saying this is its remaining life. So that's one of my observations. I don't know if other people have different experience or whether they want to disagree with me strongly, but again, if you want to be objective about this, you have to have objective measures, and I just don't see us having those in many of these areas we're talking about.
Well, I think what you reflect is the current state of the art, but I believe that those can be addressed as part of incorporating the margin assessments and margin analysis as a sort of a normal practice in the design of a complex system. So, I mean, we can talk about that further. It's a good point that, right now, a lot of this is very hard, but that's where I would suggest that we need to develop the methodologies associated with what the Commission called for 25 years ago in the, SRM to SECI 98-144. So that's about where we are. So I think, we have answered the questions that have come up. I want to thank everybody. I thought that this might go on well past.
Well, Prasad, real quickly, one last question. The very last one I had to do with the U.S. nuclear industry's almost uniform total rejection of what I'm going to call quality systems, standards, and processes that are non-prescriptive, and in particular 9001, ISO 9001. The U.S. industry's totally rejected it, and yet the Europeans use it extensively. How do you reconcile your goal of getting away from prescriptive requirements when uniformly the U.S. nuclear industry says we want to remain under Appendix B and we want to remain under NQA1? Because that's what that says to me.
Well, thereby hangs a whole other tale, Jim, and we can pursue that discussion separately. But it's certainly a good question, and I thought I at least addressed it partially when I said that industry has not really supported performance-based approaches is included in what is called modernization these days. So, you know, that's what I see as part of the problem. So,
yeah.
Anyway, thank you